everybody, this video will be for day 7 and day 8, which is about independence. So we're going to learn what it means for events to be independent or dependent of one another. And by the time we're done with this video, you'll have 2 different formulas that can help you to check for independence. You might like one better than the other, and truthfully, you have the choice of using whatever one you'd like. But we do need to teach you both. So let's start out with independence examples that are pretty basic. Let's start with example 1. Go ahead and read over situation A and think about whether you think the events being discussed are independent or dependent. Stop the video when I ask you to do things like that and then pick back up when you're done. So example A would be dependent. If I take out a red marble and then I don't replace it, then there's no longer 7 red marbles left, there's 6. So the probability of the next one would change. So for example, on the first try there's 7 out of 12 red, but on the second try there would be 6 red and only 11 marbles left because I removed one. So that's an example of dependent. Go ahead and read over part B and see what you think. These would be independent, because if I flip a coin, it doesn't change the outcome of rolling a die. And vice versa, if I rolled a die first and then flipped a coin after, the 2 outcomes wouldn't have an effect on one another. So that's why those are considered independent. So those are some basic examples. And then here in this example 2, we'll show you how we kick it up a notch to make it more of an Algebra 2 type of a problem. So go ahead and read over the question, and then we'll start in with part A. Part A says, find the probability of getting an even number. Okay, well that's pretty basic. There are 1, 2, 3, 4 even numbers out of 8. You can write a quarter, or you can write a half. You can write 4/8 or a half. Same thing. The second one is asking for conditional probability. It's saying, find the probability of getting an even, given we are only looking at the primes. Okay, so we have to figure out what's prime and what's even. So the number 1 is neither prime nor composite, in case you didn't remember or know that. 2 is prime, it's only divisible by 1 in itself. 3 is prime, it's only divisible by 1 in itself. 4 is not, because 4 is divisible by 4, 1, 2. 5 is prime, and 7 is prime. Okay, so the question says, looking only at the prime numbers, there's only 4 prime numbers, how many of them are now even? Well, 2 is even, and that's it. So 1 out of 4 numbers is going to be even, given we're looking only at the primes. Let's look at part C. Find the probability of the evens, looking only at the numbers less than 5. L stands for less than 5. And just to remind you guys, that conditional probability that I'm looking at for parts B and C, that's what we did in the previous video. Okay, so this is the formula I'm using to arrive at my answers. So I have to figure out which numbers are less than 5 here. So 1 is less than 5, 2, 3, and 4. 5 is not less than 5. 5 is 5, so that's not what we're looking for. So looking only at these 4 numbers, because again, remember the second one is the group you're paying attention to. Only the numbers less than 4. There's 1, 2, 3, less than 5. 1, 2, 3, 4 numbers. And so how many of those 4 numbers are even? The number 2 and 4 are, so that's 2 out of 4. Okay. So part D says, which event does E depend on? E being the evens. And how can we tell? What's a reasonable test? Well, I can see that E depends on P. And the reason why, so if I just found the probability of an even, it comes out to 4/8 or a half. When I found the probability of even given we're looking at numbers less than 5, it comes out to the same probability, a half. But P changed that probability to a quarter, so that doesn't work for us. Now there's another way I can show you this. It's using a formula. That might be easier. So if what I just said in part D doesn't resonate with you, or you didn't notice that on your own, you might be able to to figure it out better using these formulas. So two events, A and B, are defined to be independent of one another if this formula is true. So if the conditional probability of an event is equal to the probability of the first one alone, and they're equal, it means they're independent. Now if I just reverse the formula around, if I have the conditional probability of an event and it's equal to the probability of, again, that first event listed, then they're independent. So if I follow this formula here, my E would be like the A, if you will. And then the P and the L would be like the B. So P of A is 1/2. And do you see how that equals this P of A and B? 1/2 equals 1/2. So P of E equals P of E given L. And therefore, these events are independent of one another. It shows dependency the other way around. If I did P of E, which does not equal the probability of E given P, that means that they are dependent because it doesn't work in the formula. Because this formula does work, it means they're independent. Okay, so we'll try some more of this on the next page. Okay, again, go ahead and read over the question in part A and come back when you're done. Okay, so if we want to see if gender has anything to do with dependence on whether or not these students like the subject, we're going to have to just check it out. Okay, so we want to see if an event of probability someone likes math is dependent on gender. So let's find the probability of math first, someone liking math. Now don't confuse plain old probability like this with what we've been doing, the conditional probability. If I want to find the probability that someone likes math, I want to know how many people like math out of this whole entire chart here. Well, there are 18 students total like math out of 57. So 18 out of 57. So now we're going to have to look at the gender. So we want to know now, does someone like math given that they are a male? And does someone like math given that they are a female? We'll check that out. So this is conditional probability, so we're using the rules like we did in the previous video. Remember, I always look at the second part first, and that is the row or column I pay attention to. So I'm just looking at this middle row here. Those are the only numbers I can choose to arrive at my answer. So out of all the males in this row, there's 27. How many like math and are male? Math, male, 10. And lastly, let's do the probability someone likes math given that they're a female. So again, look at the female row or column. It's a row. These are the only numbers I can use to arrive at my answer. So out of a total of 30, how many like math and are a female? 8. Now, in order to compare these, again, to try to make it work with that formula that's on the front page, this would be my probability of A given B, A given B. I would need to change these to decimals. So just take your calculator right now and divide these out, and you can round to wherever you need to. We're just trying to see if this fraction equals this one and this one equals this one. So take a minute to do that, and you'd come up with this is about 0.32, this is about 0.37, and this is about 0.27. Oops, that's off the screen there, 0.27. So again, we do not have an instance here where the probability of event A, liking math, is equal to the probability of A given B. Okay, and since that's not true, that means these events are not independent. Remember this formula, if it's equal to one another, the events are independent. If they're not equal, like they are in this instance, okay, that shows dependence. So is there dependence based on the gender? Yes, there is, and the reason why we know that is because it does not fit into this formula. So now we can do the same thing with social studies in part B. So we're doing the same thing with this question, now we're just doing it with social studies. So we're going to find the probability that someone likes social studies. Find the probability that someone likes social studies given that they are a male. And the probability that they like social studies given that they are a female. So now that we've done this already once before, why don't you stop the video and try to get these numbers on your own and then come back when you're done. So the probability that someone likes social studies, again, that's someone likes social studies out of this entire chart. There are 19 people that like social studies out of 57. Social studies, given that they are male, look only at the male row. There are 9 that like social studies out of 27. The female row, there are 30 total. And how many also like social studies? 10. So now, change these all to decimals as well so that we can see if they can fit into that formula. Probability of A should be equal to probability of A given B if they are independent. If they don't equal, then they're dependent. And what you get here is that 0.3 repeating, 0.3 repeating, 0.3 repeating. So what we can see here is since it does follow the formula that's on the front side of this paper, these events are independent of one another. There's no dependence whatsoever. Okay, so that was the one formula that I said you were going to learn. Now there's a second formula that we can learn, okay? And I'm going to show you where it comes from, first of all. And then we're going to go ahead and re-look at the same problems we just did a second ago, but now we're going to do it with a new formula. So this was the formula for conditional probability that we started with the other day in the other video, okay? So knowing in our independence formula that this is equal to this, why don't I replace this left side with what it's equivalent to, P of A? And then I'll keep the other side the same. And then from here, I'm going to go ahead and just cross multiply. P of A times P of V equals P of A and B times 1. So this formula here is the product test for independence. So instead of using that conditional formula above, this one to check for independence, we can also use this formula. And some of you might like this formula better, or it might be easier to use this formula given certain information, okay? So what we're gonna do now is we're gonna go back and redo part A and B using our new formula. Now you might be thinking I don't have enough room here, but that's what the next page is for, okay? So now using this formula, okay, we're gonna go ahead and redo these problems. So events A and B here in the formula would be liking math, and then B would be the gender. So if I'm gonna test it out for part A, the math one, I'm going to do the probability of event A and B, so math and being male. If they're independent, it should be equal to the probability of liking math times the probability of being a male. Now this is not conditional probability anymore, so again, don't confuse conditional probability with what this is. So out of the whole chart on the previous page, how many people like math and are male? So out of the whole chart, out of all 57 people, how many like math and are male? 10. So this is 10 out of 57. And now we want to find the probability that someone likes math out of the whole chart on the previous page. We already have that number. It's 18 out of 57. Probability that someone is male. Okay, how many males are there in this whole chart? There's a total of 27 out of 57 males. And now you can just use your calculator for this next part over here. You just multiply these two fractions, look at the decimal, and see if it equals the decimal value of this. So if you put this in your calculator, you get 0.175-ish. And it would not equal what you get over here, which is about 0.1496. Since they don't equal this formula over here, the right side doesn't equal the left side, they are not independent or therefore dependent, okay? Now I can do the same thing with the other formula for the females now. Probability that someone likes math and is a female equal to the probability that someone likes math times the probability that they are a female. All right, FEM for female. Okay, you can go ahead and get these numbers on the front side and then stop the video and check back when you're done. There are 8 students that like math and that are female out of 57. There are 18 out of 57 students that like math, and there are 30 out of 57 students that are female. And again, what happens here is that they are not equal and they're not independent. But we already knew that answer because it didn't satisfy this formula either. So now if we did it for part B, okay, use our new formula for part B, we should see that they should be independent. We already proved them to be independent using the other formula. Now we're going to do it using this formula. So for part B, take a moment and stop the video and see if you can do this for part B using your new formula, the product test. See if you can figure it out, and then when you're done, come back. So now that you're back, here is my video, or my answer key, showing all of the numbers, and it proves that they're independent. So we did this problem using both of the formulas. We used the conditional probability formula that was shown on the front of day 7 notes, and we showed that these events are independent or dependent using the second formula, okay? It does not matter which formula you choose. It might be easier to use one formula over another formula based on what you're given. So there's only one homework assignment for this, and I think it says day 8 on it. Actually, well, let's take a peek here, just so we all know what to do for homework the next day. This will be your homework for the next day. And when we meet again, we'll be doing the day 9 lesson and then assignment. Okay. As always, if you have any questions, email myself or Mr. Kenzie. We'd be glad to help you.